Welcome back to another video on special relativity. In this lesson we're going to talk about spacetime diagrams, also known as Minkowski diagrams. Spacetime diagrams are critical in special relativity because they're used to explain events that happen in different frames of reference, and also to explain phenomena that underlie special relativity, stuff that we've talked about like length contraction, time dilation, etc. A basic spacetime diagram with one spatial dimension is drawn something like this, with time on the vertical axis and space, or x, on the horizontal axis. Every point on this diagram with a fixed value of position and time, every point represents an event. Let's take a simple example. Suppose I have an object A located somewhere in space at a position x0 at time 0. If my A does not move, then its position stays the same at time 1, which I'll draw as a point up over here. If A then continues to remain stationary, it will also be at x0 at time 2, and so on. Eventually, if I join all these points to draw the path of A in the spacetime diagram, I get a vertical line. Now, the path of A in spacetime, which happens to be represented by this vertical line for this particular situation, the path of an object in spacetime is called its world line. For a stationary object, the world line is, as you just saw, a vertical line. But let's draw another spacetime diagram to show another concept. Suppose I have an object B which initially starts out at x0, but this time it moves at a velocity v towards the positive x-axis, so towards the right. This means that at some time t, object B will have moved v times t units to the right. So in this case, for an object moving at a constant velocity, the world line for that object will simply be a diagonal line. In this case, the velocity v will be the tangent of the angle theta over here, with the horizontal distance opposite the angle and the vertical distance or the time adjacent to that angle. And finally, let's suppose I have an object C that again starts out at x0 but is accelerating. So after a time t, it's over here, but after a time 2t, it's traveled a farther distance because its velocity is increasing. Object C is accelerating. In this case, the world line for C will be curving over this way to the right. So that should cover some really basic stuff about spacetime diagrams in one spatial dimension. Now I'm going to talk about some important concepts in special relativity as it pertains to these spacetime diagrams. We'll start with how light, or particles traveling at light speed like photons, are depicted on the spacetime diagram. Suppose I have a photon P1 that starts at the origin of the spacetime diagram and travels in the positive x direction. Of course, because this is a photon, it'll travel at the speed of light c. So that means at time t, the photon will have moved c times t units to the right. And if I join these points, I have a diagonal line from the origin extending like so. The tangent of the angle over here is the speed of light c. This line, by the way, is also known as the light line. It's the world line of an object traveling at the speed of light, a light line. Now, what if I had another photon P2, which again starts at the origin, but now travels in the negative x direction? I'm going to draw P2 overlapping with P1, but hopefully it shouldn't get too messy. In any case, I have a light line now going in the negative x direction, like so. Let's extend this logic even further. What if now I added a second spatial dimension with my y-axis going through as shown over here? And what if this time I had a third photon P3 that went in the positive y direction at the speed of light? Well, then I'd have a third light line that looks like this. And finally, if I had a photon P4 starting at the origin and traveling this time in the negative y direction at the speed of light, I would get a fourth light line as follows. And in general, if I drew a whole bunch of light lines going in all sorts of different directions in this two-dimensional space, I would get something that looks like this. Can you tell me, while simultaneously trying to overlook this rather messy diagram, can you tell me what shape is formed by all of these light lines combined? That's right, the shape is a cone, and this is called a light cone. It's formed by a combination of a whole bunch of light lines going in all of these different directions. And so let me draw another set of x and y axes and a vertical time axis with a light cone going through this graph. The apex, or the pointy end of the light cone, is at the origin. Suppose that I now have an object D that starts at the origin at time 0 and moves all the way out here, outside the light cone on the positive x-axis. What does this mean? Well, if I look at some arbitrary time t, then the distance along my light cone for that time will be c times t, where c is the speed of light. However, the distance my object d has traveled is clearly greater than c times t. Therefore, the object d has, in effect, traveled faster than light in that time t. It's gone further than the beam of light has. This is clearly not possible. An object cannot travel faster than light in special relativity. What one can conclude from this exercise, though, is that physically possible world lines must be contained inside the light cone. As soon as they go outside, you have an object traveling faster than light, which is clearly not allowed. Now, for the rest of my series on special relativity, I'm going to adopt a convention whereby the units of time will be in light meters. So t equals 1 light meter would mean 1 over roughly 300 millionth of a second, aka the time it takes for light to travel 1 meter. Meanwhile, the units of distance on our space-time diagrams will be in plain old meters. So using this convention, if I were to draw a space-time diagram again with a light line on that space-time diagram, then for t equals 1 light meter, the photon would have traveled 1 meter. The speed corresponding to this light line would then be 1 over 1, which is just 1. So therefore, with this convention, my speed of light becomes 1, and the angle my light line makes with the time axis is a plain and simple 45 degrees, or pi by 4 radians, because the tangent of pi by 4 is just 1. And with this convention, any other object that is not light will travel slower than the speed of light, and so its speed v will be less than 1. Now, hopefully that should give you a good enough idea of space-time diagrams, at least as an introduction in the somewhat short video. In the next lesson, I'm going to talk about transformation of space-time diagrams when we go from one inertial reference frame to another, with particular attention to how relativity of simultaneity works in these space-time diagrams. I'd like to thank the following patrons for their support, and if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Hans signing out.